Hi guys, in the previous lesson we have created the standard Simulink model including the real system dynamics with the coefficients of the A and B, and the estimator model which is implemented in the microprocessor or the computer structure or anywhere you want to. And so in this lesson we will focus on how we can create the controller design based on the Lyapunov approach, but in the Matlab Simulink applications. Okay, and so firstly we need to create another Matlab function body in here, like this one. Okay, and so we need to give this function as a name of the controller design in this moment. Okay, and so in order to design the controller, X and Z value and also T value should be given in here, because we need to create some specific reference trajectory in here, or the reference generation should be completed in this function body. Okay, and so also we need to give the U value in here at the output, and xref out should also be given at this moment. Okay, and so if we have this kind of body in here, we need to add the clock value in order to obtain the simulation time in here. Okay, and so Z also be used in here, and I copy of this Z, and X also should be used in these block diagrams. Okay, and also we need to create another goat from body in here, like this one, and so this should be set into the U value. Okay, and then we should give the U to the real system, and we should give the U value in the estimator model. Okay, and so if we have this variable, we should split or obtain the state variables in here, like this one. The X hat value should be equal to the Z1 and 1 in here. A hat value should be equal to the Z2 1, because the integrator gives us in this order of this variable. Okay, and B hat value Z3 1. Okay, and so the controller design can be accomplished by using this rule. Okay, U should be selected as the xref dot plus A hat times X square plus K times E divided by B hat. Okay, and so we need to give some specific K coefficients with the positive value K equals to the 10, and error controller should be equal to the xref minus X. Okay, and so the reference generation should also be accomplished in this section. Okay, because the reference generation is important parameters to obtain the specific values of this body. Okay, and so the xref should be assigned to the xref is equal to the bias value time plus amplitude times sin omega times t. Okay, xref dot value is equal to the bias should be expressed in here, amplitude times omega times cosine omega times or w times t. Okay, and so we have the w or omega in here 2 times p times f. Okay, and f, just for an example, 0.1 at this moment. Okay, and also the bias value and the amplitude value should also be given in here 5, and amplitude value should be equalized to 2. Okay, these are the general process to create the reference value in here. Okay, and so if we have this information in here, u internal value should be assigned to what the x ref dot plus a hat times x. A hat should be used in here because we don't have any knowledge about the real a parameter in here like this one, but we have the estimation value, a hat value, and so the controller should be implemented by using this term, okay? And plus k times error controller should be given also here, okay? And b hat should be divided by these things, and the output values u should be equalized to u int, and x ref out value should be equal to the what, the x ref, okay? X ref out is given here. And so in order to compare our performance results, we have the another block in here like this one. This is the x ref value in here, and so the x ref should be assigned to the what, the x ref, and x should also be at this moment, and so we need to add another max block in here like this one, okay? And so x is assigned in here, and this is also assigned in here, and so the scope should be added at this moment, okay? And so the whole block diagram are completed, and so if I run this code and there's no error, and so we have the reference trajectory in here like this one, 0 to 5, and so the complete reference generation or trajectory is completed or tracked by using the Lyapunov strategy, okay? And so our controller is done, and then we need to compare our results, a hat and b hat value in here, okay? And so the a out and b out should also be given in here like this one, a out a, b out should be equal to the b, okay? And so if I have this knowledge, and so the a out should be assigned to the a out in here, and b out should be assigned to the what, the b out, okay? And so the a out and b out should be obtainable from the what, these diagrams, okay? A out should be compared with the what, with the z value, and so the z can be split into the 3 parts in here like this one, and so we need to use the dmax value in here by using these terms, and so 3 should be assigned in here, okay? And so the first term is to what, the a hat value, and the second term, the first term x hat value, the second term a hat, and third term is the b hat, okay? These are the order of the what, the z transform, x hat, a hat, and b hat, okay? And so if we have this knowledge about these things, and so the a hat should be assigned to this place in here like this one, and b out should be evaluated with the values of the what, the b hat, okay? And so this is also used in here. And so if I run this code, the a out is equal to the what, the 10, but a hat value is around the 3.5 points, okay, or 3.6 points, but the sufficient controller is accomplished in here, okay? And b hat value is also equals to the what, the 21, but the R stability rule gives us the 7.6. This is not a real number, but we don't have any use of the stability conditions in here, because the equilibrium points are important to initialize the system characteristics. And so if we have this information in here, and so 11 and 19 can be given at this moment, because the A is equal to 10, B is equal to the what, B is equal to the 21. And so if I run this code again, and so we have the 11 to what, the equilibrium point 9.7, okay, and B hat value is also equals to the what, 20.5 is equal to the this term, okay. And so how can I be expressed or these conditions in here like this one? Firstly, we need to create a much more rich reference generation in here, okay. And so if we have this condition in here, and so if t value, for example, greater than equal to the 5, and so x ref should be equalized to the what, the 10 value in here, for example, okay, and x ref dot is also should be 0, or we can give the another term in here 7, and so if t greater than equal to the 7 plus t 9, and so x ref may be assigned to the what, 3, and x ref dot is equal to the 0. These are the method to what, to differentiate to what the reference trajectory in here, because if we have this kind of information in here, and so we can have, or we will have the much more different or the changing variable in the x ref dot. And so how can this change the results of the A and B value in here like this one? Firstly, you need to remember that these terms is equalized or stabilized in this term body in here like this one, okay. And so if I increase the parameters of these things, and so this state values goes to the what, the 10, or B is equals to the what, these terms. And so how can we change the AM value in here like this one? If I decrease the AM value in here and so the stability condition is what, the oscillation term in here, and so the reference tracking performance is like this one, okay. And so B hat is also what, it's an oscillation term, because the gamma value is much more higher than the stabilization term, okay. And so if I change the gamma value in here, and so the reference is broken, but the always the track the reference signal in here like this one, and also A is what, is much not more stable, okay, like this one. And so if I increase the AM value or stabilization term in here like this one, and so the AM is goes to what, 9.5 point, and B is equal to the what, is around the 20, okay. And so what about the exact conditions? Suppose that you can give the A is equal to the 10 and B is equal to the 21. These are the exact values of the A and B, okay. And so if I run this code, and then you should notice that there is no error in here, and so the both signals are upon the other signal or equals to the 10 or 10, and so there is no learning rule at this moment, and the performance of the controller is what, the proper or perfect, okay. And so what this tells us, it's important to know that we have these values in here like this one, 10, 1 or 21.1, So it's so close to equilibrium point. And so if I run this code like this one, and so the points is closest to what? The R terms in here, and the other terms is closest to what? The 21.1. okay, and so Lyapunov stability gives us to what? The perfect control, because we can measure the X, but you may not sure about the what you will obtain the proper values or the exact values of the A and B, unless A and B are correct. This shows us completely that I'm talking about. Okay, and so these are the nonlinear explanation of the estimation model rule, and so you can easily implement any matrix form or the state space form on these rules by using the matrix theory or the another else. And so you can build any model by using this structure with the estimator model, because in the microprocessor structure or in the real applications you don't have any knowledge about the A and B, but only you have the equilibrium points of these things. And so if you want to obtain the unknown values coming from the system with the knowledge of the dynamics, and so we may utilize these things in the real-time application, and especially in the discrete time theory. Thank you, everyone.